Yesterday we go through the geometry file through the GMS software, and you can see second step where you have to give the GDS file to the Python input where you have to import device gen. It will create the mesh file. After that, in mesh you can see node, element, and physical group are defined. After that, you have to assign boundary condition like collection of element with boundary value and method, and region collection of element with material properties. In material, you have to define the material parameters like permittivity, effective mass, and other parameters also. After that, it will create a device where you have to center data structure and physical boundary condition. After that, you have to assign solver like Poisson solver, Schrodinger solver, labor arithmetic solver, strain solver. In today's session, basically we create a planar geometry. You can see here like plunger gate, six metallic gate. You can see here we have to create six metallic gate. In between, we have to create quantum dot confinement here. After that, it will create a heterostructure below side. You can see we have to create a heterostructure like this way. First, we have to create like silicon dioxide, gate oxide. After that, we have to create film. Then again silicon dioxide with like 5 nanometer, 10 nanometer, and 50 nanometer. Let's move to the BS code. In layout file, you can see here GDS file. We have to earlier give the GDS file. No need to take any other GDS file. You can take this GDS file and create heterostructure. Type device gen Python file. First, we need to import device gen. And we have to import path lib to import path also. After that, we have to define some constant value like mesh characteristic length, size of the mesh length. We have to give in micrometer. After that, we have to also give the length of dot characteristic length. After that, we have to assign the dimension for the heterostructure like thickness, barrier thickness. We have to assign barrier thickness also. dopant thickness we have to assign, and spacer thickness also. We have to assign two unit thickness, like give the value 100. Now we have to give the path also, where you have to save the geometry file and input for the GDS text file. Script directory, it will give the path for your Python file, absolute path. And give the directory for the file also. Script directory, and after that we have to give the GDS text file, which is stored in layout folder. With gated quantum.txt file. In layout file you can see gated quantum.txt file. We have to give the output file path also, where will be geometry will be saved. Script directory, then output folder, after that we have to give the name also. And we have to assign the device generator here. File and out file. We have to give the length also. For the visualization, you can use our tutorial. We have to write another code to create a dot between dot rectangle to create dot x minimum length. We have to assign the length also for the dot rectangle coordinates in between the gates, gated quantum dots, 6 plunger gates. We have to assign the dot minimum. After that, we have to give the value also. And the dot length also. And in the y-axis for the dot length. One nine seven. And we have to create a rectangle. And we have to give the length also. After that, we can visualize also. Wait for 1 minute. we have to give here layout because our geometry file in this, and now run. You can see it created 2D planar geometry with 6 gates, first, second and third, fourth, fifth and sixth. Here it will create a rectangle where quantum dot confinement will be happen. If I close this, you can see it will create a rectangle. From the code you can see, after visualization we create a rectangle coordinate in between. Here you can see. If I remove this, and now run, you can see it not create a rectangle here. If I close, it will not open. If I close, you can see it create a rectangle where quantum dot confinement will be happen. After that, we have to create here heterostructure at the below side. This is a top section. At the below section, we have to create substrate, barrier thickness, and other parameters. Let's create this. After creating a rectangle, now we need to relabeling surfaces also. Like we have to give the name dg.relabel surface and assign the surface also. Like in same way, when we created a geometry file, we have to give the physical surface. In the same way, we go through the code also in device here and give the surface value. Like top gate 1, same for the gate 2 also, and we have to give here surface 1. Here we have to assign surface 6 and bottom gate 1. Same for the bottom gate 2 and give the surface here 4. Now again use the visualization function. First normal, then it will create rectangle. Now it will leaving the to see the option geometry, surface, volume, and click on physical name. If you click on this, you can see top gate 2 here given, top gate 3, top gate 1, bottom gate 1, bottom gate 2, and bottom gate 3. You can see If you click on the mesh and click on 2D, you can see the 2D mesh structure also. Let's close this. And now let's create a heterostructure. We have to assign here thickness value also. Like dg dot new layer, and we have to give the thickness value for the cap, and for the cap layers also. And we have to label its cap. Now again we have to create a new layer for the barrier thickness, and for the dopant layer also. You can see first we have created the thickness value, and the same way for the barrier and the dopant also. We have to give the label here, dopant layer. Now we have to assign the new layer for the spacer thickness also. And a dot region also. Dot region. Now we have to create a for a substrate also and to generate thickness also. We have to give the label here. And give for the dot region also. For the substrate, we have to create the for the substrate also. And for a dot region. Now we have to visualize and see the heterostructure. There is some issue. Let me see first. Which one?
Just sort of like a wire like these
Okay.
or something smaller to the BNC cable.
Okay, okay.
Like, you know, kind of working.
I will need to set some decisions.
Okay.
Mostly in the table. Or somebody might have taken to the another layer.
Okay.
That's the only thing. Yeah. No. Will be written right. It is.
Wait for a 1 minute. Let's run this. You can see first it create the normal DDS text file where 6 gates are present. Now it created the dot region rectangle. Here you can see, and it will be relabeling the surface where it will assign the gate number, gate 1, gate 2, gate 3, top gate 1, top gate 2, top gate 3, bottom gate 1, bottom gate 2, bottom gate 3. Give me 1 minute.
Okay.
show some issue. Here first we will create a normal GDS text file and then create a rectangle here. After that, relabeling the surface like top bottom, top gate and bottom gate. Now you can see it create a heterostructure stack at the below section. If you click on the 3D mesh, you can see quantum dot region, gate, top gate and bottom gate. If you go to the tool, then option, then mesh, now you can see it create a heterostructure like substrate at the top section, substrate, barrier, thickness also. And if you click on 1D structure, you can see it created a dot region here. If you go to the geometry, physical names, volumes, you can see from this we have to create the heterostructure like gate oxide and film and silicon dioxide again. You can see after heterostructure we have to visualize also and setting up the ohmic band. You can see for band, and we have to save in gated.mesh file in a mesh folder. If you click on mesh file, you can see gated.mesh file. Now let's move to the second simulation. We have to simulate a Schrodinger solver and Poisson solver and find the eigenfunctions. You can see first from QTCAD device package we import some module like constant module for elementary charge like Boltzmann constant, elementary charge, Planck constant, vacuum permittivity. You can see here electron mass. After that, from QTCAD device mesh 3D, we have to import mesh and submesh. For defining the device region, we have to import mesh and submesh region. After that, from QTCAD device package, we have to import input-output file to save and load the data into output folder and input folder also. In the same way, from QTCAD device package, we have to import material as a empty, and after that, to define the material and permittivity, effective mass, and other parameters. And from QTCAD device, we have to import device to create a device structure and sub-device structure also. In the same way, from QTCAD device package, we have to import solver like Poisson solver and their parameters also. In the same way for the Schrodinger solver and their parameters. After that, we have to import analysis to plot your graph like line cut plot and band structure, band diagram. You have to use import analysis module. After that, for path, you can see here path, defining the path. We have to import path light function. After that, we have to give the input file here. You can see we have to give gated quantum gated.mesh file which created earlier just before this heterostructure stack. It will take the heterostructure stack and load the mesh file, and it will plot the mesh.show function. You can see here. After that, it will create a device. Let's visualize first. Run this. You can see from heterostructure it created a mesh structure This is a quantum dot region, and at the top, gate present and heterostructure. After that, you can see it will create a device using our mesh file, and conference carrier will be electron. You can change also with the hole, and you can set the temperature also. Like it work on cryogenic temperature also. According to user define, you can also define here. And after that, we have to dopant density in SI units. And after that, we have to set up material file for the heterostructure stack. You can see for the cap, barrier thickness, dopant layer, spacer, and substrate also, and substrate dot region also. You can see like gallium arsenide, aluminum gallium arsenide, and you can assign the doping also if you want. Like and doping, you can see here doping, ionized dopant density, here assigning in dopant layer. After that, we have to align the band cross heterostructure interface with gallium arsenide with the function D aligned band and assign the material gallium arsenide. After that, we have to apply some potential, you can see, for the B top and B bottom also for the gate. To the gate, you can apply the potential also. After that, we have to set the work function and boundary condition here, you can see. And create a non-linear Poisson solver and set the parameters and create a submesh. If I close this, it will create a submesh structure. You can see it create a submesh. For a spacer dot. After that, we use solver like Schrodinger solver and conduction band also. You can see here, save the conduction band and electron density. After that, we use confinement potential and create a sub device for the dot region. And here you can see solve Schrodinger equation and print energy. You can see here geometry property for the quantum dot and their quantum dot size and position also you can see here. And all file will be saved in the output folder like conduction band age .btu file and electron density .btu file. You can see in output folder BTU format, eigenfunction BTU format and electron density. You can open in ParaView also. File, open. Conduction band age BTU. You can see. You can use post-processing tool and filter also to plot better way. Like surface, in point form you can also do. And in wireframe also. You can also apply some filters like line cut and plot the statistical way also. And you can also see the electron density. And in the same way, eigenfunction. Let me explain again. Through the device gen, we can create a planar structure to the heterostructure. If you have a simple planar structure, through the planar structure you can create a heterostructure and you can create a quantum dot region like this. First we have to define from device gen, we have to import device generator and import path light. After that we have to assign mesh characteristic length and the dimension also like for a barrier thickness, spacer and substrate thickness. After that we have to define the number of mesh points along growth axis and initializing the device generator. After that, we have to create a rectangle for a quantum dot confinement and create relabeling the surface also and create a heterostructure stack. Let's run the third simulation. First, we have to import some important module. You can see here from QTCAD device package. And in the same way, for the mesh 2D and some parameters like you can see Poisson solver, Schrodinger solver, and from QTCAD device you can import also quantum well. Here in this Python code, basically use Schrodinger solver and print the energy for the sub device also, like adaptive meshing at a particular region where computation will occur more and convergence will be happen more. If we move to the tutorial part, here you can see for a device package, a large number of examples have been given, like Poisson and Schrodinger simulation for a nano-R quantum dot, Poisson solver with adaptive meshing, Poisson solver with a background charges, and adaptive mesh Poisson solver combined with Schrodinger solver, band alignment in heterostructure, and you can see Schrodinger simulation of a quantum well, like spin orbit coupling, magnetic effect in simulation, multi-value effective mass theory solver, and you can see tunnel coupling in a double quantum dot in fully depleted silicon insulator plunger gate. And in transport package, you can see quantum transport master equation example has been given, and quantum transport charge stability diagram of a quantum dot, and qubit package you can see. If we simulate the MOS capacitor, like you can see self-consistent Schrodinger Poisson simulation for a MOS capacitor. First, we have to import the geometry file. You can see moscap.geo has been given. First, we have to create the mesh file using geometry file. After that, we will give input to the Python script. You can see here moscap.mesh file and some value for the conduction band is text file and first excited text file also. And you can find the band diagram and you can compare with the SHRED tool which is used for the 1D MOS capacitors, and you can compare with other tool also. You can see here. Let's run this simulation in our VS Code. First, we have to open the GMS software. Here you can see to open the GMS software, file, open, in example folder, tutorial, mesh file. You can see moscap.geo. Open this. It's basically 1D MOS capacitor geometry file. Go to the file and click on Save Mesh. and close the GMS software. After that, you can see here, first we have to import some libraries from the QTCAD device package like material, constant value, and other parameters. After that, we have to give the path value like for mesh file, and you can see for the SHRED tool, we have imported the text file and for the first excited state text file. After that, we have to assign some device parameters, and you can see the effective mass tensor and longitudinal effective mass also. After that, we load the mesh and create a device structure. Let's run this first. You can see the band diagram, and you can see here the compare with the SHRED tool also. Same for the ground state and for excited state also. In this way, you can simulate multiple examples, go through this tutorial part to learn about more like device package, atom package, qubit package, and transport package also. If you go inside the QSCIT metal, you can see a lot of tutorial has been given. First, we have to import QSCIT metal, and from QSCIT metal, we have to import the design also. First, we have to change the environment first here. You can see QSCIT metal. First, we have to activate QSCIT metal environment, and after that, we have to run. We have to select the interpreter first. After that, we have to import the twisted metal, you can see, and design the layout. Like from discrete metal library, we have to transform pocket and transparent pocket also, and root middle and other parameters. After we have to assign the material, size and center region also. And you can see after that we have to assign bus P1 for root finder. And we have to know the short transmission line to connect them to the capacitors. You can follow and you can create this structure also. Like this. You can create 2 qubit devices and 1 qubit devices also. For a QSCIT metal, you have to activate the QSCIT environment, and for QTCAD, you have to activate the QTCAD environment. Let me explain. If someone facing any issue regarding the how to simulate any example, if you want to run any example from this tutorial example, first you have to create the geometry. First you have to save the mesh file using GMS software. Open a terminal here, and first you have to activate the environment from here. Choose QTCAD. Here you can see, click on this. Now you can see QTCAD environment. Go to the terminal, new terminal. You can see QTCAD environment. Open the GMS software and go to the file, open, then example, tutorial, mesh file, and you can see band alignment.geometry file. Click on file and click on save mesh and close this. After that, run the simulation. You can see the 1D mesh structure and the band alignment through the adhesion rule and potential before setting, after setting the potential, and shifted barrier height also, and band alignment from the our rescue plus simulation software. You can see the ground state, first excited state and second excited state, and band alignment simulation with 0.5 electron volt shifting well. In this way, you can simulate your example also, and you can create any example, and you have to give the mesh file, and after that you have to give some parameter like material, and you can further analysis your device. For up to now, if anyone have doubt, please ask. I have problem with running example as shown in installation video. You can run in terminal also if you want. Click on tutorials. You can see open in terminal. First we have to activate the environment. Honda activate QTCAD. You can see from this environment, it's switched to the QTCAD environment. You can open the GMS software to save the mesh file first. It will open the GMS file. file, open, go to the mesh file, like band alignment geometry file, okay, and save mesh. Close this, and you have to run here, like Python band alignment dot Python file. In terminal, you can also run. You can see the result also, like energy levels and Schrodinger equation for electron energy levels also, and their mesh statistics also, like total number of element, line element, and region physical names like left barrier, right barrier also. In this way, you can run the tutorial also. If someone has query, please ask. You can write in the chat box also. Gmail not open using terminal. Could you connect after the session, ma'am? There is an installation issue. Let me run another example. This is basically for the atomistic package. You can see from QTCAD atom package, we have import some solver. First, we have to run because it will take some time. For a time being, if you find this type of error, first you have to save the multi-scale mesh file. Wait for 1 minute. Reset report. You can see here we created a multi-scale geometry file to the concentric cylinder and rectangle. Using rectangle, basically we extrude the surfaces, and after that create the multi-scale geometry file. and create the 3D mesh structures. It will take some time to optimize the meshing 3D structure. You can see that at bottom, meshing 3D. You can see the 3D structure also, and go to the file and click on save mesh file. We have to load some mesh file. You can see at the from QTCAD device package, we import mesh and sub-mesh file. After that, from QTCAD device package, we import device package and IO package. At the now, you can see QTCAD atom package. From atom package, we create unit cell and unit cell zinc blend. After it, from QTCAD atom package, we import atoms, subatoms also, and rough surfaces also, like from atom kitting and kitting solver also. It will take some time. I show the result directly. You can see for a multi-scale germanium, it creates a band structure using atom package. Sequential turning, you can see bandage drain Fermi level also generated. Same for the off state and sequential turning also. For off state also. You can see ground state also. To write the code and see the function, we have to move to the API reference, and you can see the modules here. All module like QTCAD atom package, and if you click on this, you can see the which type of parameter you have to give, like parameters, and you have to return what return value to get for every function. You can follow this documentation, like atom package here, now device package, and qubit package, and transport package you can see here. And in the upcoming version of the QTCAD software, there is GUI also, where you have to simulate also for pre-processing and post-processing. And you can simulate large number of qubits also, like up to 10 qubits. Anyone have doubt, please ask. Who are working on DFT-based software, we also have DFT-based software like Nanodecal and Rescue. In 5 minutes, we'll also show the DFT-based software, Nanodecal and Rescue. You can also simulate like material for a device creation, graphene-based devices, nanomaterial, and TMDC materials, and other material also. For QTCAD, if anyone have doubt, please ask. Okay, now we have to switch to the material-based software, which is DFT-based software, Nanodecal and Rescue. This is a device studio GUI where you can create your material file and simulate your material file also. And you can create material, simulate and delete, add or atom here in this device studio GUI. It is a DFT based software, Nanodecal and Rescue. In simulator you can see Nanodecal and Rescue software. Here you can see the project section where you can see the pipeline of your project and you can see the properties of your material file also, like lattice area, lattice coordinates and their value also. And in job manager, you can see the condition of your script, like in running condition or in queue condition. At the top section, you can see toolbar option like file, edit, build, simulator and window help. At the below section, you can see the toolbar option for creation of atom and delete atom. If you want move to the file option, you can see import option. To import your material file, there is two options, import local and import online option. If you click on import local, our software provides wide range of material file. You can see 0D material, 1D material, 2D material, 3D material, and organic material. If you go inside the 0D material, you can see some molecule like amorphous. In the same way for the crystalline also. And same for the 1D material also. You can see with different core vector nanotube operations. Same for the 2D material also, like some novelty material like black phosphorus, boron nitride, and graphene. In the same way for the 3D material, you can see some conductor material and insulators, layer materials. You can see layer materials WSE2, MOSE2, MOS2, and metal oxide also. Like novelty material, you can see perovskite material also present, topological insulator material also present, and half metal material also present. In the same way for the semiconductor, let's import silicon first. You can see silicon, and you can see here our software support wide range of material format like XYZ, CIF, postcard, SCF input, JSON file, molecule, PDB. This type of material format our software support. You can import any type of material like XYZ, CIF format. Click on open. It will import the silicon material file. You can see here. And you can see the properties also, total number of atom, total area of lattice, and their vector coordinates also. Again, if your material is not present in local database, you directly move to the import online option. And you can search here like gallium arsenide. It basically fetch data from the material project. You can see import from material project. If you click on search, you can see with different space group, it fetch the data like gallium arsenide with different space group. You can import any material file, and you can see the properties also like cell length and their coordinate also, alpha, beta, gamma value also, and click on add. You can see there is two ways to import your material file, through local database and through online database. Like you can see import local, import online. If your material file is not present in local database and online database, you can create your own material file. You can see here new and crystal. By defining the space group and Brevis lattice like ABC, alpha, beta, gamma, and their fractional coordinate, you can create your own material file here. Like if I click on plus icon, by default carbon is selected. If you click on carbon, it will open the periodic table. You can choose any element like silicon, and you can add n number of atoms and give the value also like 0.2. I give the random value, and you can click on primitive cell, conventional cell, and click on preview before building. You can see the structure also, and Now you can click on build. It means there is 3 ways to import your material file. First, through import local database, and through import online option. If material is not present in local database, online database, you can create your own material file through the file, new, and crystal builder. From this, we have to assign the space group. You can see multiple space group are present, and you have to give the value like ABC, alpha, beta, gamma, and their fractional coordinate also. After that, if you want to redefine this crystal, click on build, and here you can see redefine crystal option. Click on this, and you can redefine and create the supercell structure. You can also create face center structure and body center also. Click on preview. You can see it creates the supercell structure for a silicon crystal. Click on build. You can see if you want to replace any atom with other atom, like create a doping, if I click on this, you can see at the top many toolbar are enabled. If I click on this, replace atom, and if I choose the nitrogen here and click on OK, you can see it changes to the nitrogen atom. If I click on this, you can also see in the properties section nitrogen atom. In this way, you can create also doping. And if you want to delete this atom, click on this and click on delete atom. It creates vacancy here. You can see. In this way, you can create also. And if you want to delete multiple atoms, you can also do. Create a rectangle and delete. You can see. You can see the different view also. XY view, XZ view, YZ view, YX view, and ZX view. Again, if you want to move to build option, you can see molecule 2D option, molecule option. If you click on molecule option, it will create a new tab. Here you can create a 3D molecular structure, like if someone working on biological molecules. Here you can see biofragments are given, multiple biofragments are given, like you can see, and some R group fragment also present here. In the same way, ring fragment also, like benzene ring, and multiple ring fragment are present. If I click on this, you can see it imported a benzene ring. And if you want to replace hydrogen atom with other atom, you can also do. Click on plus and click on nitrogen and single atom and click on this. You can see it changes to the nitrogen atom. And if you want to add hydrogen atom, click on add hydrogen. Clicking on this, you can add multiple hydrogen atoms. And if you want to change the bond length of any atoms, you can also do. You can see a modify bond. Click on modify bond. Select any atom like this one and this one. You can see it selected 1 and 2 atom. For this, you can change the bond length like this. And you can fix one atom also, like fix atom 1, atom 2 will be moved. You can see in this way. And you can also change the bond also, like single bond, double bond, resonance bond also, and click on OK. And you can change the angle also through this modify angle. You can see you can change the bond angle and click on apply data. You can see it enables the force field calculation like UFF, GFF, MF94. Click on GFF. It will optimize the molecular structure. It will take some time. Now you can see it will optimize the molecular structure. In this way, you can create the 3D molecular structure also. There is option for 2D molecule. You can see molecule 2D option. Click on this. It will open the new tab. You can see here fragments are present here. Multiple fragments. You can see. Click on cyclohexyl. And if you want to add single bond, click on this, draw single. And in this way, you can draw a single bond. And you can also replace any atom. Like with oxygen, you can change. By clicking on the carbon, you can replace. And click on apply data. You can see the structure is not optimized. Go to the force field calculation and click on GFF. You can see it optimized the molecular structure. There is two options, molecule 2D and molecule option. You can create the molecular structure also. Here you can see graphene nanoribbon and nanotube structure. If you click on graphene nanoribbon, you can see you can create a nanoribbon structure also. Like by default, carbon is selected and side B also carbon is selected. If you click on carbon atom, it will open the periodic table. You can choose any element. Let's go with the default one, carbon. And same for the side B also, carbon. You can change the bond length also and passivate with the hydrogen band, and you can see n cross m. You can give the n cross m and create like zigzag graphene, armchair graphene, and click on preview. You can see it passivates with the hydrogen atom also. Here you can see hydrogen atom, hydrogen atom. Click on build. After that, go to the build and redefine crystal in C direction and click on preview. You can see it create the nanoribbon, graphene nanoribbon structure with the hydrogen passivation. In this way, you can create a nanoribbon structure also, graphene nanoribbon structure. And there is option for the graphene nanotube. You can also create a nanotube structure also. In the same way, here you can see side A, carbon selected, side B is carbon selected, and you can choose bond length according to your need and structure type like with different core vector like N and M. Click on preview. You can see it created nanotube structures. Click on build and go to the redefine crystal like 10, preview, build. You can see it created a nanotube structure. And again go to the graphene nanotube. You can choose different element also like nitrogen, and you can increase the core vector 5 cross 5, preview. Choose also for side with nitrogen. Now preview. You can see nitrogen nanotube structure. Click on build. Again you have to redefine. You can do this redefine crystal. You can see nitrogen nanotube structure. click on build. If you want to create a concentric nanotube structure, you can also do. Go to the 2x2 nanotube structure, click on this home icon and left click of the mouse, select all atom and you can see a copy. Click on copy, go to the 5x5 nanotube and paste here. You can see a nanotube structure for a carbon. Select carbon nanotube structure and you can see center. Click on center. Now you can see it created concentric nanotube structure like carbon and nitrogen. You can see. In this way you can create also. If someone want to create the for a MOS2 nanotube structure, they also can do. First, we have to import material file. To import online, you can also import MOS2. Click on search and let's import the first one with this space group and you can see the property here also. Click on add. If you want to delete unnecessary atom, you can also do. Select this and click on delete. And you can also do in the center. And go to the build option. You can see nanotube structure. Click on nanotube and you can define like 3x3 preview. Click on build and again you have to redefine. In this way you can create nanotube structure of any material file like MOS2, any other material file. You can create nanotube structure also. Again in the build tab there is option of interface builder. Here you can create interface between two different material files. Like click on interface builder. You can see you can choose structure A and structure B. If I click on three dot and choose the material file from material folder like 3D material, and if I choose layer material like boron nitride for the first material, and for second material if I choose MOS2, lattice mismatch, you have to import same lattice. You have to go 2D material and let's import graphene. And here material, 2D material. Now you can see mismatch 9.41%. If you increase the N range, it will decrease the your mismatch value. Now you can see mismatch 4%. Click on preview. You can see the structure interface between boron nitride and graphene structure. And you can increase the like strain first surface, second surface, you can also do. And click on build. In this way you can create. And if you want to move atom also, you can also do. Select. And here you can see move atom option also. Click on this and you can move. You can see. In this way, you can create a substrate layer, thickness layer also to move atom and delete atom also. Again, in the build tab, there is option for the field junction with atoms and CAD2 atomic. If you click on the CAD2 atomic, select a square box. You can add n number of box and right click, click on set. Here you have to assign the material file like 3D material. Let's choose the conductor here. Let's choose silver and assign the length like 3 nanometer per second. Let's choose gold and assign length 1 nanometer. For the third, again choose silver and give the length like 3 nanometer. Click on calculation and click on preview. You can see in this way you can create a heterostructure stack also like silver, gold and silver. You can add multiple by clicking on plus and you can import your material file here. Click on build. You can see. And you can see the property also total number of atom, area of lattice. If I move to the silicon and in simulator, you can see Nanodecal and rescue software. Nanodecal is used for the device and material simulation software. If you click on Nanodecal, first we have to calculate self-consistent field calculation. Click on SCF calculation and you have to give electron temperature, energy cutoff like in electron volt, Rydberg and Hartree. And you can also see the exchange correlation function like LDA, local density approximation, GGA, and you have to give the K point sampling. Iteration control, tolerance value for the density matrix, Hamiltonian matrix, and you can see the maximum step number and mixing variable. In basis set, you can see local density approximation, double zeta polarized. It is also user defined. If you want to import your own basis set, you can give the own basis set in NAD and MAT format. Our software provide also basis set like in neutral atom database. You can see some basis set are present here like local density approximation, double zeta polarized for all elements. Let's go with the LDA double zeta polarized. Here you can see LDA plus U, local density approximation plus Havardio term for a rare earth element. If you click on this, you have to give the SPDF value for the rare earth elements. And in spin type, you can see no spin, collinear spin, and general spin. If you want to find the magnetic properties of your material file, click on the general spin, and you can include spin orbit interaction also. Let's go with the no spin this time and click on generate file. Here you can see in the project pipeline, it created a folder, silicon folder, then nanodecay crystal folder, and in nanodecay crystal folder, SCF input file. Right click, open with, you can see it created a script to the this GUI where all parameters are given like temperature value and energy cutoff value, exchange correlation function, and K space grid number. Right click and click on run. In the job manager, you can see nanodecay crystal SCF input file in running condition. You can see the process also by clicking on this. It's not started yet. Again, go to the simulator, Nanodecal, and you can see the analysis. Click on analysis, and you can see multiple parameters you can find like density of state, effective potential, total energy, band structure, charge, Hessian, phonon band structure, electron density, potential, eigenstate, full band structure, effective mass, thermoelectric transport, modulus, force, and stress. You can find this type of property. Let's find band structure. And in band structure, you can see symmetry K point and number of K point. If you click on path, it will open the blowing zone path. You can see. You can also delete and add also by clicking on this and move up and move down also. You can do this. Click on preview, then apply. Same for the density of state. You can see K point sampling. You can increase the number of K point to improve the accuracy and the number of energy point, and you can project according to the atom, orbital, or angular momentum. Click on generate file. In the project pipeline, you can see it created a band structure input file, density of state input file. You can see band structure input file and density of state input file. You can see also the script. If you want to change in the script also, you can also do by changing this way and click on save. You can change through the script also. First, run the band structure input file. You can run also parallel and density of state. You can see in the job manager SCF input in running condition. After that, band structure input in Q condition and density of state input in Q condition. First, it will complete the SCF input. Then after that, band structure input will be in running condition. Then density of state will be in running condition. You can also connect to the your cluster system if you want. Through this operation, you can connect to the cluster and run on the cluster also. It will take some time. For a timing, let me show the other feature also. Here you can see disorder graphene-like structure. You can create a disorder graphene-like structure for a site A, site B also, and you can assign the bond length and supercell structure. Like you can create disorder graphene structure also, and click on build. In the same way, you can create zinc blend structure also. You can choose different atom also. And click on preview. In this way, you can create. You can see the icoset drawn. You can increase the number of cell also, and you can choose the element like this, and you can increase the cell also like 3. In the same way, keyboard drawn. You can choose element like nitrogen. Increase the number of cells. and click on build. You can see a graphene nanoribbon structure. If you want to create a device for a graphene nanoribbon, you can also do. Here you can see convert to device option present. Click on convert to device option. You can see left electrode, right electrode, bottom, top, front and back electrode. Here in device studio, you can create 6 proof devices like all electrode, left electrode also, right electrode also, bottom electrode, top electrode, front electrode, back electrode. Click on left electrode, right electrode, and you can change the length also according to your need. Like if I give here 3 angstrom and click on preview, you can see it created a left electrode region, right electrode region, and center region. Click on build. It will create a graphene nanoribbon devices. If you move to the simulator nanodecal, you can see now it enable a transistor also and IV curve analysis. You can plot the find the transistor property related IV curve also and other parameter. First we have to calculate SCF calculation. In SCF calculation, we have to define like electron temperature, energy cutoff, exchange correlation function, counter integral. You can see now you can see electrode tab also. In electrode tab, you can see you have to define voltage also and electron temperature for the right electrode and for the left electrode. Same for the iteration control. You can see tolerance level, density matrix, Hamiltonian matrix, and the maximum steps also. In the same way for the basis set also, you can go through the by element and by atom also. If you want to give by atom, you can also do by atom basis set. And in spin type, no spin, collinear spin, and general spin. Let's go with the no spin this time and click on generate file. You can see it created a 3 folder. First for the device, then left electrode input file, and right electrode SCF input file. First we have to run left electrode SCF input file, then right electrode SCF input file. After that, device SCF input file. Then it will find a properties also. Let's see the properties for the silicon here. You can see it created a band structure. Right click, show view. Wait for 1 minute. You can see the band structure for silicon. And you can also export also like file. You can export in image format also. Like you can see multiple image format you can save. And you can see file, export all data. In the text format, you can also export. And you can see the number of band also, Fermi energy and other parameters also. In the same way, for the density of state also, you can see silicon density of state. You can also export in image format and text format also. And if you click on this density of state, right click, here you can see open containing folder. Click on this open containing folder. It will open the path of your material, path of your project. Here you can see it created some mat file like band structure.mat file, density of state mat file, and calculated result.mat file. Nanodecal has to written in C and MATLAB so that some dependency on MATLAB to see the band gap value and other parameters. We have to switch to the MATLAB and see the result also, like for the band gap and other parameters. And same for the density of state and total energy. You can see total energy.mat file. You can also run the nanodecal rescue in MATLAB also, and you can also simulate in MATLAB also. In the build tab, you can see bending of device. If you want to create a bending of device, like you can see you create bending of device also and create a bending of sensor. You can create a sensor devices like both side. Click on both side, and you can increase the theta value and click on preview. In this way, you can create a bending of device structure also. You can increase the angle also and preview. You can see and click on build. You can see in this way you can create a bending of device structure also and find the result also. Again, let's move to the device of graphene nanoribbon. If I move to the simulator, here you can see nanodecal. Click on nanodecal, and here you can see analysis. Click on analysis. Now you can see electrode type is device. You can find the property like density of state, effective potential, total energy for your device, scattering state, transmission, photocurrent, IV curve, charge, electron density, potential, conductance, thermoelectric current, Seebeck coefficient, AC conductance also. If I click on this, you can see option left electrode and right electrode option also. If I click on left electrode, you can find the property of left electrode also, like density of state, effective potential, total energy, band structure for left electrode region also. If I click on photocurrent, you can see photocurrent parameters like polarization basis, polarization vector. You can select also linear polarization, elliptical polarization, oblique elliptical polarization also. And you can give the photon energy range also. And you can select edit area. You can select where where photon will be strike and click on generate file. You can see in the device it created the photocurrent input file, psc.input file. If you want to create a transistor, go to the nanodecal, you can see transistor option. Click on transistor. You have to give the dielectric value and the source and gate type and you have to select, and you can create a transistor by applying gate voltage, and you can find IV curve and the transistor related properties also. You can see here relax. You can optimize the structure you also by clicking on this relax. You can see method, molecular dynamics and conjugate gradient. You can select anyone like molecular dynamics, and you can select number of gate, and you can optimize your structure also. Let me show other software which is rescue. Rescue is used for the material with simulation software. It is based on density functional theory and density functional perturbation theory, where you can find optical properties, phonon properties, and other parameters also. Let me show you. You can see rescue. Click on rescue, and you can see DFPT, density functional perturbation theory. Click on this. In the task, you can see you can find phonon band structure calculation, phonon density of state, optical property, Raman property you can find. Like you have to give the parameters and you can generate. In rescue, first you have to generate SCF calculation. Click on SCF calculation. In exchange correlation function, you can see multiple exchange correlation functions are given, like GGA, meta GGA, and hybrid exchange correlation function also given. You can see hybrid GGA and HSC06 also present. To find the accurate band gap, you have to select HSC06. You can see, and it's support also GPU acceleration also, iteration control and basis set. Click on generate file. In the same way, you can see in project pipeline, it created the rescue crystal folder. In rescue crystal folder, it created SCF input file and atom.xyz coordinates. In atom.xyz, you can see the coordinate value of your silicon material file. You can see it. And in SCF input file for the rescue, you can see their parameters. If I click on SCF input file and click on run, in the job manager, you can see in the job manager, SCF input file in running condition. Again in rescue, you can see relax method. If you click on relax, you have to optimize your structure. You have to switch to the relax module. In relax, you can see there are multiple methods: cosine Newton, conjugate gradient, and apart from that, there are multiple like high gradient, conjugate, molecular dynamics also present. We have to switch, and we have to relax your structure also. If you want to relax your structure, like relax calculation for crystal, you have to move to the this tab, relax structure. Let me show you some simulated result. Wait for 1 minute. For up to now, if anyone have doubt, please ask. If someone working on DFT based software, if someone want trial version of this software, they can contact us regarding this Nanoacademic and rescue software. We can give the trial license also for 1 month or 2 months for DFT based software also. If someone working on the DFT based software. For up to now, if anyone have doubt, please ask. If anyone have doubt related to the DFT-based software, please ask. You can write in the chat box also. No, QTCAD and DFT-based software are different. In DFT-based, we have a different software, which is Nanoacademic and Rescue. Nanoacademic is used for material and device simulation for nano devices, which is based on density functional theory and non-equilibrium gene function. And second is Rescue software, which is used for material-based software and which is based on density functional theory and density functional perturbation theory, where you can find like optical properties, Raman properties, phonon properties also. And with the multiple exchange correlation function like hybrid exchange correlation function, meta GGA, and other exchange correlation function also. Someone asking for the single wall carbon nanotube as a channel material in field effect transistor, what parameter input output we have to give? For a field effect transistor, first you have to create the geometry file through the device gen or the GMS software. After that, save mesh file, and you have to import some packages. Like if you want to find the property for transport properties, you have to import transport package and device package, where you have to import some modules, and after that you have to define some parameters like gate source voltage and other parameters. After that you can save in the video format and PNG format, also text format. You have to save your file like conduction bandage, valence bandage, a band diagram, IV curve if you want to find, and confinement of potential. You can do this. If you follow the tutorial of the QTCAD software, you can easily simulate FET. There are some examples related to the FET also. Anyone have doubt related to the DFT base or QTCAD? Please ask. You can write in the chat box also. Anyone else who have doubt, please ask. You can see the set force modules, absorption, deep diffusion, and emission thermal. And in the upcoming month, we organize this free online 2-day hands-on workshop for a organic semiconductor perovskite for LED. You can register here, and you can also give like 1 week license and certificate provided also. We provide 1 week license for set force software and law software, where you can find absorption, deep diffusion module, and advanced optics also.